Okay, this is chapter 6, random variables and probability distribution. So we're talking about binomial. This first section is all about the binomial. It's something you've at least maybe seen before. We did binomial theorem in Algebra 2 during the probability chapter, so you might at least be familiar with some of the idea of it. But we're definitely going to learn a new command in the calculator you never learned probably in Algebra 2, and just a little bit more about it. Okay, so a binomial setting arises when we have n independent trials, so they have to be independent of each other, some chance process where there's some kind of success or failure. So a binomial means success or failure. There's no other outcome. You either succeed or you fail. These are the four conditions. So to check and see if something is binomial, first, is it binary? Is there only successes and failures? Now we can kind of like finagle this a little bit. In other words, coin flipping, heads or tails. Heads wins, tails loses. That's pretty obviously a binomial setting. There's two outcomes, success or failure, if you're trying to flip heads. Rolling a die, though, what if you're trying to roll a 5? You could look at that in a binary way. So you could say rolling a 5 is success, not rolling a 5 is failure. So there's a 1/6 chance of success and a 5/6 chance of failure. So you could, a lot of things can be viewed in a binary method or binary kind of way. Independent, so trials must be independent of each other. That means the first trial has no effect. It cannot predict the outcome of the second trial. The number must be fixed. So you have to have a fixed number of trials. I've flipped the coin 5 times or whatever it is. You also have to have the same probability of success every time you flip the coin or every time you do whatever operation you're doing there. We memorize these 4 things by saying the word BINS. So it's like our acronym, or I'm not sure what it's called, but I remember with BINS. So I think about those 4 things. That's something you have to check in a lot of problems. So just to see, is this binomial or not? So genetics say that the genes children receive from their parents are independent from one child to another. I think that's true. Each child of a particular set of parents has probability of 0.25 of having type O blood. Suppose parents have 5 children. Count the number of children with type O blood. So let's go through the 4 things. Is it binary? It seems like success here is having type O blood. Not failure is not having type O blood. So it is binomial as far as binary. Are they independent? It says they're independent, so we're going to trust that. Is the number fixed? So we have exactly 5 kids, 5 trials there, so it's fixed. And is it the same probability of success? Every time they have a kid, it's a probability of 0.25, it says. So it seems to be a fixed probability of success. So yes, that does pass all the tests. That is definitely a binomial setting there. Classic. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. So is it binary? So it seems like we're trying to get aces there. So aces is success, not aces is failure. So it does seem binary in nature. Let's look at number. Is the number fixed? So we have exactly 10 cards we're turning over, so the number is fixed. Do we have the same probability of success? Well, let's talk about independent first, but I'm not sure we have that. So independent, are they independent of each other? So if I flip over an ace first, I'm lucky, get an ace. Now there's 51 cards left. I think there's only 3 aces left. So I did have a 4 out of 52 chance of getting an ace, and now I have a 3 out of 51 chance. Like that, it's not the same probability of success every time. It's not independent of each other. The second draw is dependent on the first draw. So this is definitely not a binomial setting. Shuffle deck of cards. Turn over the top card. Put the top card back in the deck. Ooh, that's important. Shuffle again. So it's the same deck to start with, essentially. Repeat this process until you get an ace. Count the number of cards you had to turn over. Okay, so now this might look promising for binary. Let's see. So binary is success or failure, getting an ace, success, failure, not getting an ace. They seem to be independent of each other because they're starting over every time. They're reshuffling. It's like a fresh deck of cards every time. Is there, so same probability of success. So every time you pick a card, there's a 4 out of 52 chance of getting an ace. And is it a fixed number? So repeat until you get an ace. That is not a fixed number. So you just keep going, keep going, keep going. Sorry, but that's not binomial, right? There's no fixed number of trials there. Okay, so the blood type scenario in part A is a binomial setting. So we're going to say the random variable X is the number of children with type O blood. X is a binomial random variable. So we've established, we've done the test for this, that it passes all 4 tests here. It's called a binomial distribution. And if you want to write this down, you can. So I think just the terms you might need to know. The number of trials is N. How many trials are you doing? 5 rolls of the dice, whatever it is. Probability of success, P is probability of success, whether it be getting an ace or rolling a 5 or whatever you're trying to get. Okay, so each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose the parents have 5 children. What is the probability of exactly one of the 5 children has type O blood? So first I'm just going to show you this. I don't know how helpful this is. I really use the formula almost exclusively here, but they're trying to do this problem without the formula. See if the reasoning makes sense to you. If it does, this is great. So you want to get exactly one child with type O blood. So the number of ways you can get one child with type O blood out of 5. So there are 5 different ways. Maybe the oldest child has type O blood. Maybe the second oldest child has type O blood. Maybe the third, fourth, or fifth, or essentially the youngest has type O blood. So there's 5 different ways you can do that. There's a different way of thinking about this than using the formula. You want one child with success. So success is a 0.25 chance of happening, or 25% chance of happening. So there's going to be one success out of the 5 kids. The others, I hate this for them, they're failures. They don't have type O blood. So it would be 0.75 times 0.75 times 0.75 times 0.75, and you get your answer. If that didn't make sense to you, don't fret. We're going to use a formula for this. So I think the reasoning, though, might just help your understanding a little bit of what we're trying to do. The formula, like the notation we use, we say the probability that random variable X, which is a binomial random variable, is equal to some value K. In this case, we want to get one kid who has type O blood, so K would be 1. Oh, here's kind of this is almost like the formula. We're getting closer to the formula. It's not a bad formula, actually. I think I like this better than no formula, which is the first way they did it. So the number of ways to get K successes in trials are starting to formalize this a little bit. I do like the formula better, just to be honest. Success probability to the power of K, so the number of successes you want. And so if you don't succeed, you've got to fail. So that the exponent of the failure is going to be the total number minus the number of successes, which would be the number of failures. So if you don't succeed, you fail, because it's binomial. So if you're 5 trials, 5 kids, we want 1 is our K, so the failure probability would be 5 minus 1, or 4. So all the rest of the kids are failures. Okay, so this is the actual formula that you want for this. We notate this, so I just need to write this down here so you see it. So we say that N comma K, they wrote it like this. N, why am I having trouble writing here? Sorry about that. Okay, so they write it like this, N, K. What you're used to seeing in calculator talk is a command called NCR. We'll talk about it in a minute, but that's a command that you might be, so technically in this setting it'd be NCK, just because they're using K instead of R. I prefer R, just because that's what the calculator says. To get to NCR, you would go to, let's see, menu, probably 6, distributions, whoops, 5. No, it's not under there, is it? NCR is not there. Okay, so let's try let's see. Let's try probability. There it is. So it's a combination or a permutation. So NCR is a combination and PR is a permutation. So we would want, so menu 5.3 is how to get to NCR, and it has the NCR command, and you put N comma K, whatever those numbers are. So that's menu 5.3. That's the commands to get to those. Okay. Oh, and I think I wrote it there, right? NCK is the formula for NK. So that's a combination. It's a calculator command. Technically, the calculator is doing the calculation. It says there n factorial over k factorial times n minus k factorial. But my goodness, why type all that in when you can just use the NCR command to type that in for you? Definitely, that's not a fraction. The NK means NCR there, or NCK technically. Okay, so again, I almost want you to think that N over K thing is NCR. So this is the formula basically, where that's, NCR is the N over K there. P is the probability of success, which means 1 minus P is the probability of failure. You might have seen that. Sometimes I would have written this more like this. NCR, I think in Algebra 2, probably something, you learn something like this. It'd be P to the R times Q, because Q is the probability of failure, which is 1 minus P to the N minus R. That might be the way you learned it. It's a P there. So that's the binomial theorem. It's just the same thing. They're using K instead of an R. Instead of NCR, they're writing N over K, but it's the same formula. Okay, so let's try to apply it. So genetics say that genes of children received from the parents are independent from one child and another. Each child's particular set of parents has a 0.25% chance, or 0.25 chance of having a type O blood. Suppose these parents have exactly five kids. Let x equal the number of children with type O blood. Find x equals 3. Interpret this value. So this is definitely binomial. It passes all the tests, fixed number of trials, same probability, 0.25. You have they're independent of each other, and their success or failure having type O or not. So let's do this by hand, maybe first if we can. So we want to find exactly 3 times. So using NCR, this would be N, I'm just going to write the formula, NCK times P to the K. It just helps me to see it. Q is 1 minus P to the N minus K. Okay, so this would be NCR, so it's 5 trials. We're choosing 3 of them. The probability of success is 0.25. To the power of K, which we want exactly 3 wins there, times the failure, which is 0.75, if success is 0.25, to the N minus K, which would be 5 minus 3, or second power. So if you did that in your calculator, you should get the right answer. We'll try it, see what happens. Okay, so NCR, I already have it set up, menu 5.3. So 5,3, because 5 trials, we want exactly 3 of them, times 0.25 to the third, times 0.75 to the, I'm just going to say 5 minus 3, you could just say 2 there. We should get 0.87, 0.087. Let's see if that's the right answer. 0.087891. Yes, there's an 8.8% chance that exactly 3 of the 5 children have type O blood. Again, we're just plugging into a formula there. If you did NCR separately, it would be like if I choose 3 separately, it would be 10, and that's what they did. They typed it in separately. I would just type that in all together and get your answer all in one swoop. Okay. Now we want to get suppose the parents would be surprised if more than 3 of their children have more than 3. So what is more than 3? I want to find the probability of more than 3. So I really want to figure out 2 probabilities here. So really you're thinking about, you could have 4 successes or 5 successes. Those would both work. So you're going to have to add up 2 things. So you're going to do NCR with 4 in there first. So it'd be 5 choose 4 times 0.25 to the, I want 4 winners, times 0.75 to the first, plus you're going to add, calculate with 5 there. So this would be weird, 5 choose 5, I think that's 1 actually, times 0.25 to the fifth, and 0.75 to the 0. Anything to 0 is 1, so that doesn't really change things. You're going to add up those in your calculator, and you should get the right answer. You can see they wrote it like that. If you wrote NCR on your test, instead of so 5 choose 4 on your test, NCR, instead of 5 over 4 like they wrote it, that notation, that would be perfectly fine. But I need you to know that notation they're using, that it means NCR, because sometimes the answers look like this. Like sometimes they don't put the answer 0.01573. Sometimes the answer is the second line there. Like just leave it kind of unworked out. They don't even use their calculator at all to get this. But it's a very small chance of having more than 3. So there's only 25% chance of having 1 every time you have a baby. So it's going to be pretty unusual to have more than 3 kids with type O blood. I don't even know what type my blood is. I think it's pretty common though. To compute binomial probabilities on the TI Inspire, it should say, we do this. So this is the way to calculate this on your calculator. So if we want only 1 value, like we want exactly 3 successes in this case, you're going to go to binomial PDF. So get your calculator out, and you go menu. It says 65A. So if you could scroll down to A or hit the letter A here, binomial PDF. So there's only 1 outcome I want. It's going to be binomial PDF. How many trials are there? I think there were 5. Probably success was 0.25. And the number of successes I want, that's the X value, is 3. So if you do that, you should get the right answer of 0.087891. And it kind of does this stuff for you. So except identifying the pattern. If you'd rather just do binomial PDF, wow, that's really helpful. And so you can just type it in just like that. Binomial CDF is when you see these problems, if you want 3 or more, say, for example, then I would use CDF, so a range of values that I want. So you go menu 65, and then if you scroll down to the B value, there's CDF. So there's exactly 5 trials, 0.25 is the probability of success. Let's say you want 3. Tell you what, I'm going to calculate what we just calculated. I think we just did 4 or 5. So you can say 4 for your lower bound, 5 for your upper bound. It should do that problem that I forgot what the result was. 0.0156. Remember, it was 1.5%. So you can calculate when it's a range of values, always use CDF. When it's just 1 value, use binomial PDF. So that's the difference between those. You can see it's written up here. So when X equals K, it's PDF. It's in red there. And in blue, when it's CDF, that's just when you have a range of values. So less than equal to a number or greater than equal to a number, that kind of thing. So these are just steps. Show your work, to find, that was funny, there's no space in there. If you use binomial PDF or binomial CDF, just label not only write down the command of what numbers you put in, but what those mean. And again, the wizard kind of tells you that when you go through the wizard, when you go to menu, 5. Sorry. Okay, that's fine. So you get the wizard tells you, if you don't know what N is the number of trials, P is the probability of success, X value is we call it X, but truly the number of successes you want. So I would write it that way probably if I were writing it. Be sure to answer the questions asked. 100% right there. Okay. So local fast food restaurant is running a draw a 3, get it free lunch promotion. Draw 3, get it 3. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. I love this. This is great. Computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, which is a 4 out of 52 chance, 1 out of 26, 1 out of 13 chance. Otherwise, the customer must pay the bill. Oh man, this would be amazing. I'm going to eat here. Just the win. Oh, that'd be great. Get a free meal. On the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 win a free lunch. So you could do this using the calculator, right? That's a range of values there. So we're going to say that menu 5, 5, and then B. So the number of trials, 250, I guess, right? Probability of success is 1 out of 13, I believe. 1 divided by 13, I hope that'll work. Lower bound, fewer than 10 free lunch. So 0 is the lowest. Fewer than 10 would be 9 is the highest, I think. So I think the answer should be 0.006129. Let's see what they get. 0.006129. You got it. So again, they just typed it in there. They said 4 out of 52 instead of 1 out of 13. I just simplified my fraction. I don't know why they wrote it like that way. CDF, so you put the range of values, the lower bound and the upper bound. So you can see when we did that, if you look at the calculator, we have 0, 9 at the end there. So we would do lower bound, upper bound. I think the TID4, they made this out of TID4, and it's not as robust of a calculator as far as stats is concerned. In fact, only 9 customers won free lunch. Does this give convincing evidence the computer program is flawed? So let's think about it. 9 is in this range of values that is less than 10. So 9 is in that range. There's only a 0.6% chance, less than 1% chance, less than 1%, 0.006, that's 0.6% chance of this happening. So I think the computer program is wrong. It seems like this is too unlikely. It's less than a 1% chance that fewer than 10, because only 9 customers won a free lunch. I think they're scamming it here. So this program is not actually randomly working. It's just spitting out not as many winners as it should be. Okay, that's your lesson for the day.